Welcome to problem session 3 in the Digital Electronics Problem Solving course on IEEE. I am your instructor Sachin from the Indian Institute of Science. Last class we left at problem number 2.14 in the textbook Digital Design by Maurice Mano. This class will continue from problem 2.15. Let me open the textbook and write down the problem. I'll copy down the problem. So we are starting with problem 2.15. Alright, let's start. Simplify the following Boolean functions t1 and t2 to a minimum number of literals. That's the question. And the functions are given via a truth table. There are three inputs which can take on 2 power 3 different input combinations. That is 8 different and the function t1 has a 1 1 1 0 0 0 0. I missed an input combination, so let me correct that. 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So that's 8 combinations. T1 has a 1 for the first 3 input combinations and a 0 for the remaining input combinations. T2 is the opposite of that. It has a 0 in the first 3 input combinations and a 1 in the remaining input combinations. So they want us to simplify T1 and T2 to a minimum number of literals. First, we have to write down the function. T1 is sum of min terms. The min terms are those terms corresponding to a 1 in the truth table. So a prime b prime c prime plus a prime b prime c plus a prime b c prime. Then to simplify this, so a plus a equals a in Boolean algebra, so we can write this as a prime b prime c prime added twice plus the remaining terms, and then we can group as follows. Then we can take out a prime b prime common in the first group, a prime c prime common in the second group. Now we know that a plus a prime is 1, so c plus c prime is 1 and b plus b prime is also 1. That's another law of Boolean algebra. So we get T1 is equal to a prime b prime plus a prime c prime. We can take out a prime common to get a prime into b prime plus c prime. So this has 3 literals. That's the minimum number of literals for T1. And if you observe the truth table, we can see that T2 is 0 whenever T1 is 1, and T2 is 1 whenever T2 is 0, T1 is 0. So T2 is the complement of T1. We use the De Morgan's theorem or De Morgan's law, and we can write this as A prime whole prime plus B prime plus C prime whole prime. This will become A plus B prime prime and C prime prime. It will become A plus BC. So again this has 3 literals. That's the minimum number of literals for T1 and T2. Next we will go to question 2.16. The question is the logical sum of all minterms of a Boolean function of n variables is 1. Part A, prove the previous statement for n is equal to 3. Part B, suggest a procedure for a general proof. Solution: for part A, let us assume ABC to be the 3 variables. The sum of minterms is A prime B prime C prime plus A prime B prime C plus A prime BC plus A prime third term was A prime BC prime plus A prime BC plus A B prime C prime plus A B prime C plus A BC prime plus A BC. The first 4 terms we can take out A prime common. We'll get A prime into B prime C prime plus B prime C plus BC prime plus BC. The last 4 terms we can take out A common. We'll get B prime C prime plus B prime C plus BC prime plus BC. For the terms in the bracket, again we can take out or first let's simplify the outside. You can see that the terms in the bracket are same for both A prime and A. So using distributive law, we can rewrite this as a prime plus a and b prime c prime plus b prime c plus b c prime plus b c. A prime plus a is 1, so it's 1 times b prime c prime plus b prime c plus b c prime plus b c. Now again in this expression we follow the same procedure. The first two terms we take out the first literal common, so we can write this as b prime into c prime plus c plus b into c prime plus c. And again you can use the distributive law to write this as b prime plus b and c prime plus c. Now b prime plus b is 1, we will be left with c prime plus c. C prime plus c is again 1. So that concludes the proof for part A. Next we have to construct a general proof for this. So suppose we have f is a function of n variables and the variables are x1, x2 up to xn. Then similar to the procedure we followed in the previous question, we can write f of x1, x2 up to xn as the sum. This is using Shannon's decomposition. X1 prime into f of x2, x3 up to xn plus x1 into f of x2, x3 up to xn. This is nothing but x1 prime plus x1 into f of x2, x3 up to xn 1 times f of x2 to xn. Now we can use if f of x2 to xn is equal to 1, then f of x1 to xn is equal to 1. Also we have shown f of x1, x2, x3 equals 1. So we can use induction to show f of x1 to xn is 1 for all n. So if it's true for 3 variables, it should be true for 4 variables also, because if you take the first literal in the 4 variable, uh, if you take the half of the terms in a 4 variable sum of all min terms, and the first half you take a x1 prime common, the first literal common, and in the second half again you take the first literal common in each term. Then you can use distributive law similar to this to write it as uh, a prime plus a into the remaining terms. Now the terms remaining in the brackets will be the sum of all min terms in a lower order function. That is, if you start out with a sum of all 4 variable minterms, then by taking the first literal common in half of the terms each, you will be left with uh, 1 times the sum of all minterms of the 3 variable uh, in 3 variables. So again, if you take in half of those terms, if we take the first literal common, then you will be left with the sum of all minterms of 2 variables. So you can keep repeating in this way until you simply get the sum of all minterms in a one variable schema, which will simply be in a one variable expression, which will simply be uh, the variable plus the complement of the variable, which is 1. So this is sum of all minterms with one variable c prime plus c, that will become 1. So you can use an inductive argument to prove the result. Okay, since they only asked for a general procedure, we won't write down the exact procedure, we'll leave it at that. And we'll go to question 2.17. Question 2.17 is the following: obtain the truth table of the following functions and express each function in sum of min terms and product of max terms form. Part A is b plus cd into c plus bd. Part B, the function is cd plus b prime c plus bd prime into b plus d. Part C, the function is c prime plus d to b plus c prime. Part D, the function is bd prime plus acd prime plus ab prime c plus a prime c prime. Solution for part A: the function is b plus cd into c plus bd. There are 3 variables b, c and d. So I can write this as, by using distributive law, bc plus bd plus cd plus bcd, and then you So here they are saying you have to obtain the truth table and then express in sum of min terms and product of max terms form, but it is actually easier to write it in a sum of min terms and product of max terms form and then write the truth table. So I'll do the reverse. And to write it as a product sum of min terms form, what you do is you introduce each of the variables in each term. So the first term has only BC, so you have to introduce D somehow. To do that, you can multiply that term by D plus D prime. Since D plus D prime is 1, the term won't change. You do the same thing with the other terms also. But last term has all three variables, so you can leave it as it is. Now you use the distributive law to expand this. And you write down all the terms, and you write down the repeated terms only once, because sum of a term with itself is the term itself. A plus A is just A, and AB plus AB is just AB in Boolean algebra. So the terms are, it would be easier if we write it in order. There's no B prime, C prime, D prime term. There's no B prime, C prime, D. There's no B prime, C, D prime. B prime, C, D is min term 3, M3. Have B prime, C, D. You don't have B, C prime, D prime. We don't have B, C prime, D. We have B, C, D prime, that's 6. Then you have B, C, D. So that's M3, M6, and M7. So from that you can write the truth table B, C, D, and F. That's M0, so it's a 0. M1 has 0. M2 has a 0. M3 has 1. M4, M5 both are zeros. M6 has a 1 and M7 has a 1. So that's the truth table. Now to write it in the product of max terms form, you can simply look at the zeros in the truth values of F, and whichever input combination gives you a 0, that should be present, that max term should be present in your function expression. So the terms in the product of max term form are B plus C plus Z and B plus C plus D prime. So the max terms will be of the form of the sum of variables, and if in the corresponding input combination, say for here you have a 0, so this input combination must be present as a term in your expression, and all the variables must be present in that term. So you have B, C, D. And then if in the input combination you have a 0, then corresponding to that variable you have the uncomplemented form. So since all of B, C and D are 0 in the first input combination, you have B plus C plus D. All of them are uncomplemented. In the second term you have D is 1, so D will be complemented. B plus C plus D prime. Once you know the procedure, you can simply fill out the other terms, B plus C prime plus D, and these two terms, B prime plus C plus D and B prime plus C plus D prime. That's the product of max terms expression for this particular function. Just making sure there are no mistakes. So there was a mistake here. There is one more term which is B C prime D, which is M5. That means there's a 1 in this position, and so that term will not occur in the product of sums expression, so that term is not there. So the sum of minterms form has four terms, and product of minterms form has the remaining 4 terms. Okay, that's the procedure. There are 3 more parts. We'll just go through them quickly. I won't explain much in each of those. Part B, you have CD plus B prime C plus BD prime and B plus D. You use the distributive property and you get 4 terms, BCD plus CD plus B prime CD plus BD prime So I have already eliminated the repeated terms. Again, there are only 4 terms here. This is 7, M7, M3, M6, M4. M0, M1, M2, M3, M4, M5, M6 and M7. So that's the truth table for the function, and the product of sums form will be of course this can be written as summation m of 3 4 6 7, and this will be product capital M of 0 1 2 5. So that expression will make it more general by removing the name of the variables. The variables can be named however you want. Similarly, here also you can write this as sum of 3 5 6 and 7, and this will become product of 0 1 2 4. Okay, part C, part D are left to you as homework. You follow the same procedure except that in part D there are 4 variables A, B, C and D. So each term should contain all 4 variables, and you'll have 16 input combinations and 16 minterms and max terms. Okay, we'll move on to question 2.18. For the Boolean function f equal to xy prime z plus x prime y prime z plus w prime xy plus wx prime y plus wxy. Part A, obtain the truth table of f. Part B, draw the logic diagram using the original Boolean expression. Part C, use Boolean algebra to simplify the function to a minimum number of literals. Part D, obtain the truth table of the function from the simplified expression and show that it is the same as the one in part A. Part E, draw the logic diagram from the simplified expression and compare the total number of gates with the diagram of part B. Solution. First we have to write the truth table. For that, let me write down the expression again. There are 4 variables w, x, y and z. So there are 16 input combinations. Let me write down the possible input combinations first. Okay, the way we uh, fill up the truth values of f just based on this original expression is we take each term and we see for which input combinations each term will become a 1. So if for some input combination if a single one of these terms becomes a 1, then since f is a ORing of all these terms, f will also be 1. So if you look at the first term x, y prime, z, that will become a 1 if x is 1, y is 0 and z is 1. So for 0 1 0 1, x, y prime, z will be a 1, so f will be 1. Similarly for 1 1 0 1, x, y prime, z will be 1, so f is 1. So if it has only 3 variables, then there will be 2 input combinations which will give you a 1, which will make that 3 variable term a 1, which will in turn make your function go high. Second term is x prime, y prime, z. So if x is 0, y is 0, z is 1. That's here and here. Third term is w prime xy. That's if w is 0 and xy are both 1. So that's this term and this term. Fourth term is w x prime y. So w is 1, x is 0, y is 1. That's this and this. Finally wxy, all three of wx and y should be 1. So this and this, and rest of the input combinations will give you 0 as the output because none of the terms in the function are 1 for the rest of the input combinations. So that's how you write the truth table given Boolean expression for your function. Part B was to draw a logic diagram for the original function. So I'll write down the original function again. Hello. The original function was x y prime z plus x prime y prime z plus w prime xy plus w x prime y plus w xy. We can get the complemented form of each of the variables by using a NOT gate. So in the further circuitry we have, I'll just assume w prime x prime and y prime are directly available to me. So when the function is expressed in a sum of products form, so each term can be produced by using an AND gate. Since there are 5 terms, you will need 5 AND gates and since each term has 3 inputs, 3 variables, you will need 3 input AND gates to realize each term, and then the function is the sum of all these, so you will need many OR gates with less fan-in, or if you have one OR gate with a large fan-in, you can just use one OR gate to get the sum of all those terms, and that will be your function f. So 6 gates in total. Part C, we have to simplify this. So let me copy down the expression again. And just to make grouping simpler, we'll write wxy twice, which won't change the expression. We'll take out y prime z common in the first two terms. We'll take xy common in wxy, one of these wxy and w prime xy, and we'll take wy common in wx prime y and the other wxy term. So that's why I wrote the last term twice. So this will just become y prime z plus xy plus wy. To make it even simpler, I can take y common and write this as y prime z plus y times x plus w. So that's the simplified expression. Part D, you have to get the truth table for this expression. So we'll follow the same logic. If any one of the terms becomes 1, then your output function will become 1. And for the first term to become 1, first term is y prime z. So if y is 0 and z is 1, the first term will become 1. Second term is y and x plus w. So if y is 1 and x is 1, that term will become 1. Or if y is 1 and w is 1, that term will become 1. Or if y is 1 and y, x and w all three are 1, then the second term will become 1. So let's write down the input combinations first, and we'll come back to the function value later. Now y prime z means y is 0, z is 1. That's here, 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 those four. Xy means x and y both are 1. So that's this and this, this and this. Wy means w and y both are 1. That's this and this, and this, which are already covered. And remaining input combinations give a 0. So if you compare with the earlier truth table, 0 1 triple 0, 0 1 triple 0, and followed by 3 ones and a 0. Here also 3 ones and a 0, followed by 1 1 1 0, 1 1 1, 1 1 1 0, 1 1 1. So the truth tables match. So the simplified expression also gives you the same truth table. So it's the same expression. So whichever one you implement, you'll at the end get the same function as your output. So in that case, if the simplified expression leads to a smaller circuit, then you can use the smaller circuit for implementing the function, or we call it realization of the function. And let's see, with this expression y prime z, you need a y prime, so one NOT gate will give you a y prime. One term is y prime z, the other term is y and x plus w. These two terms are all together. So you needed, other than the NOT gate, 1 2 3 4, 4 gates excluding NOT. Here you had 6 gates excluding NOT. Fan in was 3 and 5 for and OR gate respectively. So each gate was should be able to take more inputs, so it should be able to act as a drain for more input values. Here fan in is 2 for all and OR gates. So the circuit that we get from the simplified expression is much simpler and is preferable while implementing it in real life. The point is that both circuits will implement the same function. So you're not getting anything by using more gates really. It is actually costing you to use more gates. Okay, we'll move on to problem 2.19. Express the following function as a sum of min terms and as a product of max terms, and the expression given is in four variables. F of a b c d is b prime d plus a prime d plus bd. Solution: first we will introduce one variable extra in each term. So what I am doing here is I am writing this as a plus a prime into bd. Since a plus a prime is 1, the expression doesn't change, and then I use the distributive law to distribute bd to both a and a prime. I'll get a bd plus a prime bd. Then I'm doing that for all the terms. Next, to each of the terms, again I introduce the variable that is not present in the term. That is a prime b prime cd plus a b prime cd and then I'll remove the repeated terms. And write the terms in order. Have a prime b prime c prime d, which is m1, plus a prime b prime cd, which is m3, plus A prime B C prime D, that's M5, plus A prime B C D, that's M7, plus M8 is not there, M9 is there, A B prime C prime D, M10 is not there, have M11, A B prime C D, M11, and M13, A B C prime D, have M15, A B C D. So that's the sum of minterms form. You can write it as summation of the minterms 1, 3, 5, 7, 9, 11, 13, 15. And which is the sum of all odd numbered terms. Now to write it as a product of max terms, you write product of, since 1, 3, 5, 7, 9, 11, 13, 15 are there in the sum of minterms form, all those input combinations give a 1 in the output. So to write the product of max terms, you need all those input combinations which will give you a 0. So these are the remaining input combinations. So get product of 0, 2, 4, 6, 8, 10, 12, 14, 16. We'll go to question 2.20. Express the complement of the following functions in sum of minterms form. Part A is f of a b c d summation of minterms 2, 4, 7, 10, 12, 14. Part B, f of x, y, z, product of max terms 3, 5, and 7. Solution for part A. So f complement of ABCD, We'll simply have the minterms that are not present in f. Since there are 4 variables, there will be 16 minterms, m0 to m15, and f complement will have only those minterms which are not present in f. It's summation 0, 1, 3, 5, 6, 8, 9, 11, 13, 15. Solution for part B. First we write this in a sum of minterms form. To do that, you write only those minterms which do not correspond to any of the input combinations in the product of maxterms form. So f of xyz will be nothing but 0, 1, 2, 4, 6. And now to complement it again, you write only those terms which are not present in f. So it will be 3, 5, 7. And you can observe that the index of the terms in product of sums form, product of maxterms form, and index of the terms in the complement of sum of minterms form are the same. But remember that this is the product of maxterms, so the terms will be of the form a plus b plus c. There will be a sum of the variables, but here it's a product of a sum of products form, so each term is a product of the variables abc. So product abc, that type. So even though they have the same indices, they are different terms. Question 2.21. Convert each of the following to the other canonical form. Part A, f of xyz equals summation of 135. Part B, f of abcd product of 3, 5, 8, 11. Solution. So you simply change from a sum to a product, and if you are taking the sum of minterms indexed by 1, 3, and 5, you should take the product of maxterms indexed by all those terms which are not indexed by 1, 3, and 5. 0, 2, 4, 6, 7. Similarly for part B, 0, 1, 2, 4, 6, 7, 9, 12, 13, 14, 15. Problem 2.22. Convert each of the following expressions into sum of products and product of sums. So here they are not asking you to express it as a sum of min terms or a product of max terms. As long as they are product terms, it's fine in sum of product form, the SOP form. They don't have to be min terms. And in POS form, you don't need to write it as max terms. Just a product of some terms is enough. Solution for part A, we'll use the distributive law to write this as ux plus wx plus u prime xwv. That's a sum of product terms. Um, Next we have to convert it into a well, there's a small simplification you can do here. You can write this as ux plus wx into 1 plus u prime v. So this will simply become ux plus wx. That's the SOP form. You can take the x common and write it as x times u plus w, and that's the POS form. Okay, for part B, x prime plus x into plus y prime into y plus z prime. We can use the distribution of addition over multiplication and write this as x prime plus x and x prime plus x plus y prime y plus z prime. First term will become just 1. Again, you can use the distribution of addition over multiplication to write this as x prime plus x plus y prime and x prime plus y plus z prime. So the first term will become 1 again. So you're left with x prime plus y plus z prime. This is a sum of products. Well, a single variable, you could say, well, we consider it as a product term, and it's also the product of sums form because it's a sum of variables in complemented and non-complemented form, but they're just one term. So even if it's one term, you kind of consider it as a product of terms. Okay, so that's a relatively more interesting problem than the previous problem, so I'll mark it. Problem 2.23. Draw the logic diagram corresponding to the following Boolean expressions without simplifying them. A, you have BC prime plus AB plus ACD. That's B C prime. That's BC prime. That's AB. That's ACD. That's the sum of those three terms, which is BC prime plus AB plus ACD. Part B is A plus B, C plus D, A prime plus B prime, B plus D, you have A plus B, you have C plus D, have A prime plus B plus D, we have a product of those terms. Part C is AB plus A prime B prime, C D prime plus C prime D. So first expression is an XNOR gate, AB plus A prime B prime. Second expression is an XOR gate, C prime D plus CD prime, and the product of those two. C XOR B complement into C XOR D. Part D, A plus CD plus A plus D bar into C bar plus D. You got A, you have CD, you have A plus D bar, C bar plus D all together, A plus CD, and these two should have been OR gates. A plus D bar, well, these two should have been AND at first, right? That will give you A plus CD, A plus D prime, C prime plus D, that's A plus D prime and C prime plus D. Go to question 2.24. Show that the dual of the exclusive OR is equal to its complement. So x OR of x and y is x y prime plus x prime y. So let's say that's f. Dual of f dual is x plus y prime and x prime plus y. So you replace the AND with OR. There's an AND here, there's an AND here. Replace those with ORs. You replace the OR with AND. And you use the distributive law to write this as x prime plus xy plus y prime x prime plus y prime y. X prime and y prime y are 0, so this is xy plus x prime y prime. That's the dual. The complement is xy prime plus x prime y complemented using De Morgan's law. You can write this as xy prime complement and x prime y complement. This is nothing but again De Morgan's law, x prime plus y and x plus y prime, which we saw earlier. X plus y prime and x prime plus y is xy plus x prime y prime, which is equal to the dual. Problem 2.25. By substituting the Boolean expression equivalent expression equivalent of the binary operations as defined in table 2.8 show A. The inhibition operation is neither commutative nor associative. Part B, the exclusive OR operation is commutative and associative. So first we have to see what is there in table 2.8. Let me copy that down real quick. We have 2.8 inhibition for part A, f is equal to x prime y, or you can write this as f of xy equals x prime y. That's inhibition. Or you can write this as, if it's a binary operation, dot circle x circle y is x prime y. Now y circle x is y prime x, which is not equal to x prime y. So inhibition is not commutative. So the commutative, an operation circle is said to be commutative if x circle y is the same as y circle x. For example, addition in normal arithmetic, 2 plus 5 is 7 and 5 plus 2 is 7. So addition is a commutative operation in the group of integers. But this inhibition operation is not commutative. How do you say these two expressions are not equal? Suppose x is equal to 0, y is equal to 1, and x prime y will be 0 prime and 1, which will be 1 and 1, which is 1. Y prime x will be 1 prime and 0, which is 0 and 0, which is 0. So for the same input combination, they are giving a different output, so those expressions are not the same. Next we have to check associativity, and for that we'll check x circle y perform first, then circle z. So this is x prime y circle z. This is x prime y complemented and ANDed with z, which is nothing but x plus y prime and z, xz plus y prime z. Now if you do the operation in another order by doing the operation first on y and z and then with x, so this will become x circle y prime z, which will be nothing but x prime y prime z, which is not equal to x prime y whole prime z. So x circle y circle z, where operation is done on x and y first, it's not the same as x circle y circle z, where y and z are operated on first. So the order of operation matters. So inhibition is not associative. For part B, we have to show this with XOR. X XOR y is xy bar or xy prime plus x prime y. Y XOR x will then become yx prime plus y prime x, which is nothing but xy prime plus x prime y. It's nothing but x XOR y. Therefore, XOR is commutative. X XOR y XOR z is xy prime plus x prime y XOR z, which is xy prime plus x prime y and z plus xy prime plus x prime y complement into z. Xy prime plus x prime y complement is nothing but xy plus x prime y prime. So the expression will become xyz plus x prime y prime z plus xy prime z prime plus x prime y z prime. Now if we do the operation in the other way by doing XOR on y and z first, so it's x XOR yz prime plus y prime z, which is nothing but and we'll use the distributive law to expand this as and we'll rearrange the terms. Write this as xyz plus x prime y prime z as x y prime z prime plus x prime y z prime, which is, if you compare, is equal to x XOR y XOR z. So XOR is associative. x 2.26 show that a positive logic NAND gate is a negative logic NOR gate and vice versa. So we can show this by using truth tables. So let's say A and B are the variables. NAND gate is AB bar. Positive logic NAND will have 0 0 will give you an output of 1, 0 1 will give you output 1, 1 0 will give you output 1, 1 1 will give you output 0. That's positive logic NAND. For negative, so positive logic NOR will be of the form 0 0 will give you 1, 0 1 will give you 0, 1 0 will give you 0, 1 1 will give you 0. Negative logic NOR, so to write it in negative logic, your inputs and output are both in negative logic here. So if your input is 1, then it is considered active low, and in NOR, if both your inputs are active low, you should get an active high output. But since the output is also in negative logic, you will get a so 1 1 will give you a 0 in negative logic. Just give me a minute. Okay, now in negative logic, if you want to give low and high, in positive logic, this will be low high. In negative logic, you give 1 and 0. So 1 is low and 0 is high, and you would get an active high output, uh, a high output in negative logic. So you get a 1. So essentially, if you want to write the truth table for the negative logic, then you invert the inputs and also the output. So 1 1 will give you 0, 1 0 will give you 1, 0 1 will give you 1, and 0 0 will give you 1. Now if you interchange the input combinations and write it in the following way, then 0 0 gave a 1, 0 1 gave a 1, 1 0 gave a 1, 1 1 gave a 0. So the two tables match for the positive logic NAND and negative logic NOR. So this is enough for two input gates, but it is also true for multiple input NAND and NOR gates. A positive logic NAND is equivalent to a negative logic NOR. Let's go to the next question, 2.27. 2.27. Write the Boolean equations and draw the logic diagram of the circuit whose outputs are defined by the following truth table: F1 F2 ABC 0 0 0, both are 1, 0 0 1, it's 0 and 1, 0 1 0, 1 and 0, 0 1 1 will give 1 and 1, 1 0 0 will give you 1 0, 1 0 1 will give you 0 1, 1 1 1 will give you 1 0. Okay, F1 is A prime B prime C prime plus A prime B C prime plus A prime B C plus so the combination 1 1 0 is not there. That means for 1 1 0 you can take that as a don't care condition. So well, that won't be useful now, but in simplification using K-maps that will be useful. For now, F1 is simply A prime B prime C prime plus A prime B C prime plus A prime B C plus AB prime C prime plus ABC, and F2 is simply A prime B prime C prime plus A prime B prime C plus A prime BC plus AB prime C. Logic diagram is left as a homework. Right, problem 2.28. Write Boolean expressions and construct the truth tables describing the outputs of the following circuits described by the of the circuits and the first part is as follows. It's this is BCD prime, this A times BCD primes times E whole prime, so I equals solution A times BCD whole prime E, A times B prime plus C prime plus D prime times E, so A B prime E plus A C prime E plus A D prime E. And the truth table is listed as a homework. Part B, you have C or D or E, B prime. For part B, solution is Y1 is A XOR C plus D plus E. Y2 is B prime F into C plus D plus E. That's 2.28, 2.29. Determine whether the following Boolean equation is true or false. X prime y prime plus x prime z plus x prime z prime is equal to x prime z prime plus y prime z prime plus x prime z. So if we can find a counter example that shows that the left side is not equal to the right side, then we can easily say that it's a false statement. Otherwise, we might write the truth table and check if they are equal. But if you observe here, if x equals 0, LHS is y prime plus z prime is equal to y prime. RHS is z prime plus y prime z prime plus z, which is y prime z prime. So if x equals 0, y equals 0 and z equals 1, then LHS will become y prime, which is 1. RHS will be y prime z prime, which is 1 and 0, which is 0. So for this input combination 0 0 1, the LHS is 1 and RHS is 0. So those two algebraic expressions are different expressions. They are not equivalent. So the following Boolean equation is false. Question 2.30. Write the following Boolean expressions in sum of products form. There's just one expression it's in the product of some form. To get the sum of products, we simply use the distributive law. So that's the SOP form. The last question of the chapter: write the following Boolean expression in product of sums form. Expression is a prime b plus a prime c prime plus abc. Solution: can take a prime common in the first term, then you can write this as abc plus a prime into abc plus b plus c prime. Then again you can write this as a prime plus ab into a prime plus c This can be written as b plus c prime plus ab into b plus c prime plus c. C prime plus c is 1, 1 plus b is nothing but 1, so the last term will just go to 1. First term again you can write it as a prime plus a into a prime plus b. A prime plus c remains as it is. B plus c prime plus ab can be written as b plus c prime plus a into b plus c prime plus b. So this first term also goes to 1, and you're left with a prime plus b and a prime plus c and a plus b plus c prime and b plus c prime. That's the product of sums form. And with that we conclude all the problems in chapter 2. In the next session we'll start from problems in chapter 3 of the textbook. Thank you for watching. Good night.